Hello everyone, my name is Alberto Poncelas. I come from the Trinity Center for Literary and Cultural Translation and Adapt Center in Ireland. And I'm going to present using multiple subwords to improve English-Esperanto automatic literary translation quality. So the outline of this presentation will be the following. First, I will give an introduction and talk about Esperanto language. Then I will describe our proposal, which involves augmenting the training data to build an NLP model. Then we're going to see the results of the experiment, which are grouped into three: multiple segmentation in target, source, both source and target. And finally, we're going to give some conclusions. So the goal of this work is to build English to Esperanto neural machine translation models. Esperanto is a constructed language. It was created by Zamenhof in 1887. It has a lexicon derived from Indo-European languages like French, English, Italian, German, and so on. And it was constructed to be very regular and has a simple grammar. Typically, the words in Esperanto contain several affixes, suffix or prefix. So, for example, the word virino, which means woman, is composed of vir, which is the root for adult human, the suffix in, which indicates that it's a female adult human, and o to indicate that this word is a noun. So, although Esperanto is a popular constructed language, there aren't that many resources. And because of this lack of parallel data, we cannot build good quality neural machine translation models. So in this work, we want to find a way to improve these NLP systems, and for that, there could be several approaches. One could be to translate using a pivot language. However, in this case, it will be difficult also to find parallel data involving Esperanto in a third language. Other approach could be to generate artificial text. A popular approach could be of building this artificial parallel data would be to use back translation, where the sentence in the target side in Esperanto would be translated into English, and then this sentence could be paired to augment the training data. However, in order to create the back translated sentences, we need an NLP model. And if this model is not good enough, we risk of creating a noisy parallel set, and if we use it to augment the data, it may hurt the model in the end. So another approach could be to introduce noise, which would consist on replicating the sentence with slight modifications, and this is what we are going to follow in this work. So as we say, we propose to introduce noise by using different splits. So typically, when building an NLP model, instead of using as vocabularies, instead of using the complete words, we use subwords. And a typical example of this is Byte Pair Encoding, or BP, which is used to split these words. And this proceed by initially assuming that each character is a subword, and then iteratively the subwords that are consecutive more frequently are merged together into a new subwords. So this process of merging the most frequent subword is done iteratively and until a certain number of merge operations. So somehow this number of merge operation controls what will be the granularity of splitting the word. This means that using different BP configuration, different number of merge operations will lead to different splits. So for example, the word virino could be, depending on the configuration, could be split as vir ino or vir in and o. And our proposal is actually to replicate the sentences in the training data and apply different BP configurations. Actually, we use BP because it's a popular approach and it's language independent. So the outcomes of this work could be used for other languages as well. However, Esperanto is especially suitable for this approach because it contains, or it has, many words have different affixes and suffixes. So here the diagram represents what are the experiments that we are going to try. So in the top left corner we see a parallel dataset. This could be split with BP in, for example, 89,500 merge operation, but the same dataset could also be split using 50,000 or 20,000 or 10,000 merge operation. And what we propose is to concatenate all together into a larger training data with replicated sentence that are split differently and train and machine translation model. We have divided this experiment in three. So in the first set of experiments, we will combine only different splitting only in the target side. In the second set of experiments, the different splits will be only in the source side, and finally a combination of previous both approaches. So the experiments will be as follows. We are going to build a neural machine translation model from English into Esperanto. We are going to follow the transformer approach. As training data, we have 303,000 sentences, which is not that much. And for testing the models, we are going to use two test sets. One is books, which contains sentences from books of Edgar Allan Poe and and the book Alice in Wonderland. And the second test set is Salome, which is in a biblical domain, and actually we have taken the sentence and aligned the sentences ourselves, so we have made this Salome test publicly available for anyone who wants to use it. The test set is going to be split with BP using 89,500 merge operation, and only that. So regardless the empty model, we're going to use these two test sets split with this configuration to test it. And the different BP configuration are going to be applied only in the training data, either the target, the source, or both of them. So first of all, we build a baseline, which is a single dataset, the 303,000 sentences that we have for training data. So this means that there's one instance of each parallel sentence, and we apply the same configuration as the test set, both in the source and target side. And here in this table we have the blue scores achieved by each of the test sets. So for books, it achieves a blue score of 6.72, and for Salome a score of 18.03 blue score. And we are aiming to improve these results. So first, let's move to the first set of experiments. We are going to, as we said before, we are going to replicate the parallel sentence. We will concatenate different data sets, and in each dataset we are going to apply a different configuration of BP in the target side, and in the source side we are going to keep the same BP configuration as the test set, 89,500. And as the different BP configuration are going to be applied only in the target side, to each of these datasets we are going to use the notation TRG and the number of merge operation that has in the target side. So here we have the results. We saw all the combinations. So when, for example, in the first row there are these two datasets, a combination of these two datasets where the target side sentences have 89,500 merge operation and 50,000. And we do the same thing with 3 datasets and 4 datasets. We also remove the duplicates if after applying the BP 2 sentence pairs remain the same, we remove one of the instances. And in the right we show the blue scores of when translating the books and Salome test set. We mark in black those that are higher than the baseline, and if these improvements are statistically significant, we mark it with a star. So as we can see, most of the scores are higher than the baseline. And also note that not always concatenating more dataset leads to better results. So sometimes, for example, by concatenating these two the result can be better than concatenating 4 datasets. Now let's move on to the second set of experiments. We are going to do the opposite thing, so we are going to keep a BP of 89,500 in the target side, and we are going to use different BP approaches in the source side. And as the test set has been split with 89,500 merge operation, we are going to have at least one dataset that has this configuration. And actually, by doing this, we will expect a lower results, because as the different splitting is done in the source side, we will expect a lower matching between the source side and the test set. And finally, in this case, we are using the notation of CRC and the number of merge operation as the different splitting is in the source side. So here we have again the results, and in the right we see that most of the scores are marked in black. They are improvements over the baseline, and actually the results are similar to those of the previous experiments where the different splitting were in the target side. And the last set of experiments involves combining all the approaches seen before, so the combination of different BP both in the source and target side, and we have built a model that we have called all, and here we see that the results are again better than the baseline, and in most cases better than the previous experiments. So using different BP both in the source and target side leads to better results. And when exploring a bit further, what we see is that what is happening is that, especially the words that don't have many occurrences, by doing duplicates of the sentences and doing different splits, what happens is that these infrequent words will be seen by the NNT in different contexts. In this case, meaning contexts that they are surrounded by different tokens, because the words next to the frequent word will be split differently. And what happens is that it can better model the word. So for example, here we have the source, but she did not venture to say it out loud, and the part of venture to say in the baseline, it omits the word venture and only translate say, diris, which means say, but the word venture is omitted. However, in the models where the data has been augmented with different instances and different BP configuration, the word venture has been translated as decide, intend, or undertake, which are somehow different translation to translate the word venture. So we see that the original, using only a single data set, it will skip the word. The NNT model wouldn't be able to model properly the word. However, when augmenting the training data, the word venture is seen surrounded by other tokens in different tokens, as they are split differently, and is able to better model the word and propose a translation for that. So as conclusion, we see that combining the dataset with different configuration of BP leads to better translation. The improvements are seen when we apply not only in the target side only, but also on the source side, so both source and target. And what is happening is that the words, especially the most infrequent ones, are seen more often and in different contexts, so, surrounded by different tokens, and therefore the NNT model can model better those words. And as an additional contribution, the testset Salome, which have been aligned by us, has been made available, and you can find it in the following link. So that's all for now. Thank you very much, and I will be glad to answer your question. Thank you.